So we are here to learn about field programming gate arrays, and Carsten Becker is gonna teach us how to do that. So there can be more and merrier, FPGA programmers, because they can do more cool stuff. And I'm pleased to introduce my colleague and fellow part-time scientist, Carsten Becker. He is a local Hamburg resident and PhD candidate at the University of Hamburg-Harburg. And he learned to love FPGAs after he made his first 3D graphics accelerator in university. And he continues to pursue this line of work in his dissertation. And he also solves FPGA programming and all other electronics problems for the Google Lunar Express team, the part-time scientists, who are still in the running to be the first private organization to put a rover on the moon. So please welcome Carsten Becker.
Okay, thanks a lot. I think the introduction was very thorough, so I can just skip this slide. So I'm going to talk about FPGAs because I really love them a lot, and you can do really like everything with them. It's just very hard to do. No, wait, I wanted to motivate you. It's not so hard, but you just need to know what you're doing. And I want to show you what you can do with those, or where they excel at, and what are the use cases where they're not so good at. And essentially, what is an FPGA? It's a programmable logic. So you have an area that you can program, and you can do whatever you want with this. So those are a few that know binary signals. You know that if you have something like a two-input system, like an IC with 2 pins and one output, you can have 4 combinations at the inputs. And I will just call them A and B, and the combinations that you can see are very obvious. And the thing is, in programmable logic, you can set X to whatever you want. For example, on the left side, you see a XOR that is realized, that if you have 0, 0 as input, it will output a 0. If it has 1 and 1 as input, it will output a 0, and otherwise it will output a 1. On the right-hand side, you see I don't know, a NAND. Yep, perfect. And so you got the idea. So that's good. Now that you know that you can build a NAND, you know that you can build like every logic circuit possible with just those lookup tables, as they are called. So the idea is that you have in an FPGA you have those lookup tables where you have some inputs, and you can describe what the output should be. And the fun begins when you realize that one of those outputs can be the input of another lookup table. And then you create a network of lookup tables, and then you can create even more complex logic. This is the basic idea how an FPGA works. In reality, it looks a bit different. Note how it says that this is a simplified vertex 6 slice. So what you can see, there are 4 lookup tables on the left. Then there are some multiplexers which are selecting signals, and then there are some registers, and yeah. So it's not as trivial as I may sound with just the lookup tables. It's a bit more complicated, and I'm going to tell you a bit about it. So with the lookup tables, you can, for example, make a very simple adder. And you can have an input signal that is like 4 bits, and you add a 1, and you get another output signal that is 4 bits as well. And the question is, how do you, for example, implement a counter? If you use the input of your adder, then there's the adder, and use the output of the adder and feed it directly into the adder as well, then you have a combinatorial loop, and it will do nothing useful. And to avoid that, because we want to do something useful with FPGAs, there's so-called registers. Registers are like data storage. You know that your CPU, for example, has a clock. And what it does is on every rising edge of the clock, it does something interesting. It stores the data that is on the input, and a little bit later, it puts it on the output. And it just captures the input at a very specific moment of the rising edge. And with that, you can have your logic, that is combinatorial logic with the input table, with the lookup tables, and put that into a register. And then you have another portion of combinatorial logic, and then you can have another register, for example. Or you can create a feedback loop. For example, if you want to realize a counter, you have your 4 digits, and you add 1 in your combinatorial logic, and you put it as a new input for the register. And the reason this works is because the time it takes for the combinatorial logic is not small, not infinitesimally small, but has a certain delay. And so it will arrive ideally arrive prior the next rising edge, but after the rising edge actually occurred. And so this way you can create a counter, and this way you can realize all kind of interesting synchronous designs. For example, you can create a CPU with it and do some other fun stuff. And I will talk about what you can do with it later. And especially I will talk about why an FPGA can beat an i7 in certain tasks, even though it is running at a frequency that is significantly lower than what the i7 is running at. So when you have a CPU, you have like 3 tasks, A, B, and C. And you can sequentially execute those. And if you want to decrease the time that it takes for those 3 tasks, you can actually increase the frequency of the CPU, or you can make the task shorter by making them more efficient. In an FPGA, you have actually something like a blank canvas, and in this canvas you can draw your functions. So, for example, on the upper left corner, you can place 8 motor controllers. On the lower left corner, you place your CPU okay, maybe the B is a bit small for a CPU, but and maybe on the C you have your video decoder or encoding algorithm. And so the thing that you are working with in an FPGA is actually the area and the frequency. The frequency that you can run your circuit at is determined at the worst combinatorial delay that you have in your whole design. So, for example, if you want to compute, so for example, you're running your circuit at 10 megahertz, and so you have a certain amount of time between the rising edges of the clocks, where the registers are storing the data. And if your addition exceeds this time, then your timing is not met, and you cannot use the design that you have chosen to run with this frequency. You have to lower the frequency. This may be possible if your design allows it. Most of the time it does not, because you're constrained by some external clock, or maybe you're doing USB data transfer, or you have a camera that is clocking your data into the FPGA. So in this case, you need to split up the combinatorial logic into smaller blocks and distribute them, so that in the one cycle you're doing a part of the addition, and in the next cycle you're doing the next part of the addition. And so that you can increase your frequency. And area is also very difficult. If you're making blocks smaller, sometimes you're increasing the area that it consumes. And when your area is consumed, you need to buy a bigger device. So you can, So this is like, and bigger devices obviously are more expensive as smaller devices. So in reality, it's not just the lookup tables that this so-called fabric, which is the programmable part of the FPGA, is composed of. Actually, it also contains the lookup tables, the flip-flops, or the data storage registers, as they call them. It also contains some multiplexers where you're selecting between several input signals. It contains routing resources, which are very important if you have a lookup table here and you have another lookup table here and they should be connected, then there are very fast connections between those, and those are your routing resources. And obviously you can also run out of those. Usually you will also find some clock management things like a PLL, where you can have input a frequency of 10 megahertz and get out a frequency of whatever you like, usually 20 megahertz or something like this. Then there's also carry logic, which helps you to create faster multipliers and adders, which is very important, and shift registers, which are used for shifting a bit to either direction. In theory, you could realize a lot, or almost everything, with just those components that you find on the left-hand side. But the problem is making a CPU with just those components is not very efficient. And so the vendors went on to decide, like, okay, maybe it's a good idea to, for example, add a hardware multiplier. It consumes significantly less space on the die than if you're doing it with lookup tables, and it also runs significantly faster. And so they decided to put all kind of interesting stuff into what's called hard blocks or hard cores. And one of those is, for example, the DSP unit, which is actually a multiply accumulate. You can use those for all kind of interesting filters and stuff. And then our multipliers are very popular, 18-bit by 18-bit, very popular in width. You may notice that FPGAs vendors don't really care much about 8, 16, or 32-bit. They care more about 18-bit. I don't know why they chose 18. Probably have a good reason for. You will also find block RAM, which is RAM that is embedded into the fabric, so that you can have some storage, some bigger storage. They are like multiple megabit sometimes if you're like buying a really expensive FPGA. Sometimes they are just a few kilobit. And also you have some high-speed I/O interfaces. For example, with an FPGA you can attach to a PCI Express port and connect with those. Or you can attach your own SATA hard disk or your own SATA whatever. And the high speed is really high speed because they can go up to like 25 gigabit connections. Also, some vendors thought that it is really a good idea to embed a processor into the fabric or into the FPGA, which I think is a really smart idea, because then you can have your software running on the CPU, but accelerate some functions with the fabric. And I'm going to explain to you a bit about this later. Also, there are some memory controllers so that you can interface external memories like DDR, DDR2, DDR3. They are all supported. And some vendors also include some ADC, DAC, so that you can really read some analog voltage or generate some analog voltage, which you really need. And now I'm going to talk, I want to motivate you what you can do with FPGAs. And I was looking for some projects from the hacker scene that I really liked. And one of those projects is actually the Borg ventilator. I'm going to show you a picture first, and then I'm going to go back to explaining what it is. So it's essentially it's like a ventilator, but instead of fanning air, it's just having spinning PCBs, and there are like 250 RGB LEDs, and then you can attach any video source to it, and it can be displayed. And what the FPGA is doing is, it's for example doing a pixel transformation to polar coordinates. It's also doing some gamma correction, and obviously it needs to do some very precise timing so that the video is not jittering around, but is really showing at the same position always. Another very cool project that was demoed like 2 years ago. I found that very, very cool because what Bunny did was he used an HDMI input signal, and he did not decode the signal itself, but he just synced up to the HDMI signal, and put in some encrypted overlay into the stream itself. So at one point it was an original picture, and at some other point in time it was another picture. And he extracted the key and inserted the encrypted stream. And the fun thing about it is that he does not need to decrypt the content stream, which is a pretty neat trick to avoid DCMA or DMCA lawsuits, because this would violate it if you use the key that was leaked several years ago. So the question is, how do you program an FPGA? Well, okay, so this is where it gets ugly. No, I want to motivate you. This is where it gets fun. So, you can either choose a high-level tool like MATLAB Simulink, if you're coming from, if you have this installed. You can create really nice filters with it, or test runs. Also, there is a very poor attempt of automatically converting C to HDL, and the vendors are like, this is the best idea ever, and no, it's not. At least for the next 10 years. So don't do that. There is an attempt of porting OpenCL to HDL or to a hardware description language, which I think might actually work, and it might not be as worse as trying to say, just give me your C code and I will make it faster on the FPGA, which will always never be true. And so this is the very high level where you can start. Also, you can start at a hardware description level, which is what is most commonly used these days. Unfortunately, a rather poor choice of languages have been established in the space of programming. VHDL and Verilog are both very old languages. Neither of them are nice to write, in my opinion. I'm going to show you examples first, and then you will see why I'm ranting about it. So, as you can see on the left side, you will see VHDL. It's for the military contractors among you. This is ADA based. It's not like anyone cares about ADA, but this is VHDL. It has the same awfulness as ADA. It's very odd that you place all the semicolons there and but not there, and then the comma there, and then you say and there but not there, and it's very verbose as well. This makes it very confusing, I think. There's also Verilog, which is like, they sound like, okay, VHDL. Oh, by the way, VHDL was not invented for programming FPGAs, but it was invented for documenting the ASICs. And so at one point they thought like, if we are doing all the effort of, describing it, why shouldn't we like simulate it? And so they used VHDL for simulation. And then they realized like, if we are like simulating it, we can actually use it like for synthesis to put it on an FPGA or on the ASIC. And so actually you could just use HTML. It's like you're describing something, and half of what you're describing cannot be synthesized to the FPGA, which is a problem that VHDL and Verilog are sharing. And I think this is very confusing, but VHDL is very popular in Europe, and Verilog is very popular in the US. It's like a 50-50 split. I've heard that China is copying Verilog. Yeah, and there is, shameless plug of myself, there is also PSHDL, which is called the plain simple hardware description language. This is the same code as you can see on the left and the bottom. It's just shorter and not as fucked up as the others. Yeah, sorry, I really hate, I've been working at a university for a quite long time, and I've been doing what's called a hardware practicum every year. And maybe there are some students in the audience that are suffering from it right now. And every year it's the same. People are like struggling with the tools, struggling with the language because it's not so. Wait, no, I want to motivate. Okay, never mind. So after you described your design with those beautiful words, the synthesis tool will run among it and will say like, this piece that was described here with this 10,000 words looks like an adder. So I will place an adder here. And then it will go around and do this for all the code. And sometimes it's guessing wrong, so you need to find those kinds of features where it got it wrong. And then you have what's called a synthesis. And the synthesis actually translates what you have written into blocks that can be placed on an FPGA. Into lookup tables, multiplexers, shift registers, and all this stuff. And the result is a netlist. And after that, this process is rather quick. It usually doesn't take more than 2 minutes. And this is really quick. And then comes the process of place and route. If you're used to slow compilers, you will appreciate the fastness of a modern C++ compiler once you realize that your place and route can take anywhere from 1 minute up to 3 weeks. The problem is that placing the resources on an FPGA is an NP-complete problem, and fitting it into the timing that you're setting. For example, at one point you're saying, like, I want to run this design at 100 megahertz. And the worst thing that could happen is that he sees that he can fit all the logic into the FPGA, but the frequency is like 95 megahertz. And so he's like routing up, throwing away stuff and putting in trying out new ideas to see if it fits or not. And the fun thing about it is that it's depending on the seed. And the seed is sometimes the checksum of the file, and so sometimes if you're generating a file and you're changing the date in a comment, then you will get a different place and route result. And so there was a case where one vendor said, oh wait, the version that we created on the 26th works the best because the comment was the right and the COC checksum led to the best seed, which resulted in the best place and route. And so after that you have your configuration file, and so you realize that this is not called an executable because it's not. It's configuring the resources within the FPGA to do whatever you told them to do, or do something entirely else if you have a tiny mistake in your header description language. By the way, in PSHDL, what you simulate is what you get, which is not the true for VHDL or Verilog. If you're running simulation on Verilog or VHDL, it might be what you're getting in hardware, but it might be not. So one of the cool features of FPGAs is pipelining. For example, you want to you want to calculate A plus B times C plus D plus 10. And what you can do is you have your inputs A, B, C, D, and you put them onto the pipeline. And every clock, the data gets processed. You can see that the green blob is first computing A plus B and C plus D, which is then used as input for the multiply, which is then added to 10, and then you have a result. And every clock, you get a new result. This is very important to understand because this is how FPGAs are getting their I can actually kick ass regarding modern CPUs. So, yeah, after just 4 cycles, or wait, there was more, 7 cycles, you have all your compute data or your results, and yeah. Another very cool feature of FPGAs is high-speed I/Os. I was talking about those. You have tons of GPIO. Every pin that you have on the FPGA can run a UART and a SPI bus or I2 square. You know what I mean. And the other stuff. Every protocol that you can imagine, most of the protocols that you can imagine can run on every pin that you have. And those pins are actually pretty fast. So you have shift widgets just within the FPGA for the inputs. so that you can have like up to 480 or to 800 megabit on each pin as input. And then there are dedicated high-speed receivers where you can have up to 25 gigabits per second on one pin, or 2 pins actually, it's differential. So this is pretty neat, and we'll also have very precise control of the signal. So you can, for example, say, okay, I want this pin to be 3.3 volt, and I want to have this one to be 1.8 volt. And you can say there should be a pull up, there should be a pull down, and you can also say that the drive strength, which is used for creating the edge, should be like, not so high, like 1 milliampere or like 8 milliamps. You can really define how you want the signal to be. And now I'm going to compare CPUs and FPGAs, or actually the combination of them. So CPUs are good at things that you do just once. If you have a large piece of code and it just run once, then it would be a huge waste of resources to put that onto an FPGA. FPGAs are good at things that repeat very often. Yeah, large complex, you don't want to re-implement something like an operating system on an FPGA, even though I would be really appreciated to see that. If someone is really masochistic in its nature, then he can contact me and I will help him to suffer. Wait, no.
Contact with the Kinky Geeks.
I was not at the Kinky Geeks thing yet. CPUs are also very good for giving a quick shot. You're used to fast compile times. It doesn't take weeks. Just like minutes, and you can put it onto your CPU. You test it, works. If it doesn't work, you have very quick development cycles. Those are not very common in FPGA development, at least until PSHDL takes over the world. But you can actually combine those powers. So a CPU can be very good at for example, providing a network stack so that you can have, for example, a CPU can run Linux and accept some interesting data via Ethernet, and then you feed the data into the fabric of the FPGA, and you do something interesting with it. So the combination of those both is a really powerful combination. And you can also realize a CPU in the fabric itself, but the frequencies that you're getting are like 100 megahertz, 150 megahertz, sometimes 200 megahertz, which is on the very new devices, but you will not get like gigahertz right now, at least. The good news is that unlike with CPUs, where the frequency kind of stopped to increase at 2.6 gigahertz or whatever your i7 is running right now, you also in the FPGA domain, they are benefiting from the shrinking of the process so much that the frequencies are getting very close to 1 gigahertz right now in the very, very latest or just announced version. And you can also have a CPU realized in the FPGA itself. Those running at 400 megahertz or something like this. Yeah, so what you can do is you can accelerate a part of the application, and you can start with a full software implementation that you run on the CPU, and then you just identify which part is taking a long time. For example, the cipher for encrypting something is taking a long time, and then you just put it into the fabric, and then you can accelerate things. I'm going to show you an example where actually FPGA that is running at 200 megahertz can beat an i7 right now. And this is something Diploma might was about. This is about the discrete wavelet transformation that is used in JPEG 2000, which is a pretty neat compression algorithm. And the way it works is that you have a 2D wavelet that is applied to rows and then to vertical. And if you look at it in the CPU, when this looks like this. There's at the top you see the input pixel, and then they are like combined into other parts, and then at the end you get like one pixel, or actually you get 2 pixels out. So on the CPU, when you load the first pixel, it's a cache miss, and it has to go to the DRAM, load it. But there is a prefetch, and so when the next pixel is loaded and put through the process, you get a very efficient process. The discrete wavelet transformation is basically memory bound. The computations that you see at the bottom, they don't contribute much to the time that it takes for them to do. So yeah, if you do it horizontally, your pixels are all in line. Everything is perfect. You have prefetch, cache is working as expected. But the problem arises when you're actually trying to do the vertical thing. You start at memory address 0, and the next row in a 1024 pixel is at 1024. And so you have a cache miss and a cache miss and a cache miss. And so you have cache miss after cache miss. And your process, your CPU starts to become really, really slow. Like a factor of 30 or 40 if you have bad luck. And in an FPGA, what you could do is you do the horizontal DVT. You put in your horizontal pixel, and then you store the result of the horizontal wavelet in a program that is in the FPGA itself, and then you feed it into the vertical wavelet transformation. So it doesn't go back to the original DDR external memory, but it's contained within the FPGA. And those are running at full speed of your fabric, and so this way you can improve the performance significantly. So on a CPU, you have on a horizontal line you have a perfect cache hits to the prefetch. So this is very fast. In a vertical scenario, you have cache misses all the time, so you have a significant slowdown. But in an FPGA, you're performing a linear read of your image, and then you do magic with it, and then you perform a linear write on the output. And so the FPGA is running at your full memory speed, while your CPU is permanently stalled by the external memory that it has to use. And so this way, the wavelet transformation on the FPGA that we realize it takes like 50 milliseconds, and on an i7 it takes like 30 milliseconds or something like this. Even though it is running at 200 megahertz, while the i7 is running at 2.6 or even 3 gigahertz when it's clocking up. And so this is how FPGAs can kick ass versus CPUs. There's also, by the way, I put up the slides in the speaker, so if you want to look at this chart at any point later in time, you will find it online. So if you're starting a new project and you're like, oh, what should I use? You always have some obvious choices, like you have a regular x86, which is very nice to program, or you have a GPU, which is very powerful in floating point, or you have a DSP, which is like those, which is very nice to embed, and then you have an FPGA, which is very good at almost everything, but not in programming. And then you have a microcontroller, and so this chart basically is showing that it's, for example, if you want to put an x86 on your quadcopter for doing something fancy, you may have a power problem, because those are kind of power hungry, and embedding x86 processors is challenging, at least. But nowadays are good one-board computers. But if you have a 240 volt power cord going down from your quadcopter, that's not very helpful. They are very good at floating point operations, obviously integer operations and control flow stuff. Control flow stuff is all this with if and else and break and jump and continue. It is very hard to get a GPIO attached to an x86, so this is no fun. And they can't do pipelining as FPGAs can do. But the upside is they are very easy to program, and they are very easily available. But if you want to do very precise timing in the area of nanoseconds or microseconds, things get very difficult. The GPUs, you don't want to put those on the quadcopter, definitely. They are very hard to embed. They are definitely not low power. They are very, very, very good at floating point operations that can be parallelized. Integer operations as well. Control flow is like, I/O is like non-existent. Pipelining cannot be done. The programmability is like a bit better than FPGAs, but worse than the CPU. And you have absolutely no control of timing, whatever. DSPs are like very powerful for multiply accumulate applications with filter rings and all this stuff. This is what they are optimized for. They're also optimized for being embedded into a power constrained device. And so, yeah, you can see what they are good at. The microcontroller obviously is at the very low end. Like I was thinking about like an Atmel. It doesn't do very floating point operations. And the FPGA is like you can do everything, but the problem is that floating point operations are not well supported. In the latest vendor tools, they are claiming that they can do floating points, but they are very expensive in an area and frequency perspective. Control flow is like not very quite hard to do. You have to create state machines, you know, those ones that you heard about in your lectures during the university that you thought like, wow, why would I ever need that? For programming FPGAs, you need those. But you know, the I/O capabilities are like ginormous. You know, there's a 1,000 pin FPGA that you can buy, and you have like multiple hundreds, like 600 or 700 general purpose I/Os that you can use for whatever you want to. And obviously they can do pipelining, which is pretty cool. Well, the programmability is a bit challenging, but if you want to do timing, those are really, really good. You can do really precise timing up to nanosecond level. If you want to do if you, for example, want to violate the setup and hold time of registers, you can do it with FPGAs. It's pretty cool. There's also a very interesting talk about attacking ICs later at like 21:45 in SAL 1, which you should take a look at. It's pretty interesting to see. Very, very quick overview of what the market is. So Xilinx and Altera are like John Jackson and Jack Johnson. There's really not big a difference. The one is producing in the low power high performance process at TSMC, and the other one is using the high performance low power process at TSMC, and they're fighting each other over which one is the better, which is quite funny to see. But in the end, it doesn't really matter which one you take. Then there's also Actel, which is now Microsemi. Those are, oh, by the way, as Xilinx and Altera, they have like 45% each market share each, so they are very, very common. Actel are like very low power because they are flash based, unlike the Xilinx ones, which are SRAM based. The advantage of a flash based one is that you put it on and it's there, and while in the SRAM based, they need to load the configuration from an external source before they can power up, which can be a big challenge when you want to do something like PCI Express. Also, the Actel ones are used for space missions and avionics and stuff like this. So if you want to do something with radiation, I would recommend you to use an Actel. The latest one, I've never used one of those. They are there on the market. By the way, if you're interested in buying the most expensive FPGA, Xilinx has the one priced at like 32,000 euros. That is one device, probably this size. And but Altera is very close with just around about 20,000 euros, but you have to buy three. Just they don't sell it with one quantity for whatever reason.
Are samples available?
I don't think you get free sampling with those. No. If you want to head into programming FPGAs, you probably think about what board should I buy. This list is by far complete. It's just some boards that I heard about that I found interesting, and the cheap ones are actually quite well. And the one that you see in the upper left corner, which is the PSHDL board, I will introduce you that in my later talk at 21:45 in Hall 6, I guess. This should be a really cheap board at like 30 euros or 30 something euros. From the SOC is a system on a chip, which is like a CPU and an FPGA. Those are very interesting boards because, especially the micro Z board, because you have a dual core Cortex R9 running at 1 gigahertz, where you can run a perfect Linux, and then you have all the fabric as well. So yeah, and the cheapest way to buy them is by ordering the Parallella board, where you also have the very strange 16-core core that they are actually trying to sell, but only there's a Sync FPGA, which is pretty cool, and the price is unbeatable because they are putting some money into distributing those. Yeah, also there is a Datenkrake, which was introduced at Thickend this year, which is also an Actel FPGA with a microcontroller, and yeah. So if you're interested in getting started programming FPGAs, there will also be a workshop tomorrow at 9 p.m. in Hall F, where you can actually try to get some LEDs blinking. Please install the Xilinx tools beforehand. They are 6 gigabit in download, and they take 20 gigabit of your workspace, of your disk space, and they almost run on Linux. Well, yeah. So if you're interested in getting some blinking LEDs, or if you want to learn more about the PSHCL board, you can find that there. And are there any questions?
Thank you. If you have questions, please line up on the microphones. They don't have numbers, but we'll figure that out. Do we have any questions from the internet? Apparently not. So let's start with. Right there. Go ahead.
You were talking about high-level synthesis tools, and you were saying that they are actually a better idea, at least for the next 10 years. Could you go a little bit into the experience you have made with them?
Okay. So the high-level synthesis tools. Yeah. Oh no, I don't care. So there are those high-level tools that are actually generating code for you, and So my experience with the latest Vivado suite is, which is like the C2 HDL tool that Xilinx offers. I wasn't able to get anything useful out of it. There's also a C2 hardware from Altium embedded, which so in general the C2 HDL compilers, they work well for the examples that the vendors provided with them. I haven't yet seen any real-world application written with it that had a decent performance or did anything really useful with it. The MATLAB Simulink thing is a bit better because actually Xilinx is supporting them with blocks, and they do some neat optimizations. So this is the MATLAB Simulink I have seen in the wild and used successfully. So this is something to look at. There's also some open source C2 HDL translators that are working more or less okay.
The gentleman in the striped shirt.
Have you ever tried DMA with PCI Express?
There are examples that you could put onto an FPGA, but I haven't tried it personally yet. Okay. But it should be definitely possible, yes.
And the next thing, can you put the slide with your boards on it? This.
Yeah, okay.
There's a board with a CPU and an FPU unit on. Is it possible on which board have PCI Express support?
None of the boards that I listed here. There are plenty of boards with PCI Express. They are usually not cheapest one. Yep. I was aiming for boards that are rather affordable. Unfortunately, a lot of boards really start at 500 euros, which is not something that you want to spend if you don't know what you should do with it. The PSHCL board provides an answer to that. You can do blinking LEDs with it. RGB LEDs. Okay.
Thanks.
Let's take a question from that line, and after that from over there.
Not actually a question. I have a script to build Debian packages from the Altera toolchain if anyone needs it.
Oh, that's pretty cool.
I have a question regarding a specific use case, namely Bitcoin number crunching. Are there any like open source projects or anything like that? And if so, how much of resources in terms of time and money would one have to invest to get some real profit out of it? If you, I mean, I know it's a very specific question.
No, but I have a good answer for it. So a friend of mine was buying this rig of like 4 boards with a very big Spartan LX 150 on them, and he was mining some bitcoins with it. There are plenty of open source projects for it. You will find them very easily. The problem is that with the latest increase in complexity of the Bitcoin mining algorithm and the increase of ASICs being fairly good available, it's not longer feasible to use FPGAs for mining Bitcoins in a if your mom doesn't pay the electric bill.
Since we have no other people at microphones, you guys over there just go through it and until the time comes up.
Thank you for your presentation, but you said that FPGAs are good at input-output, and if you combine CPU and FPGA, you will get some nice results. But actually, there is a problem in interfaces between computer and FPGA, because if you haven't CPU core on FPGA, you will have problems. If you haven't PCI Express on the same board, so you are bound to for about 20 megabytes per second in transmission between CPU and FPGA. And where is the profit?
Well, there are definitely boards available where you have DMA address access to your host memory. So if you want. This is very possible that you put your FPGA board into the PCI Express slot, and you have the full.
I said that you haven't got PCI Express, so you can do nothing.
Well, you can have PCI Express, it's just not with the boards that I was listing here. That was my point. And also if you're using this the sync processor, as it's called from Xilinx, where you have the CPU within the die of the fabric. You have a very, very broad access to the fabric, obviously.
Thank you.
Hi, great talk. How cheap and small are they going to get? Like thinking you want to reduce complexity on the board and shift it towards software, kind of like an Arduino where I can put in like, I don't know, motor controller, FTDI, and some DSP, but I don't want to do that for 50 quid, right? So how cheap are they going to get?
Well, I think the PSH shield board that I'm going to present is like is very a lower bound of what you can have with an FPGA that is usable in a very flexible way. You can the FPGA itself costs like 11 euros if you buy it single volume at DigiKey, and it's fairly okay from a size perspective. Of course, there are very small FPGAs or CPLDs for doing I/O stuff like this. And they can go down like, 2 euros, 3 euros.
Thanks.
Firstly, just a comment on the PCIe question. The Cyclone 5 certainly is available with a hard PCIe core on die, and some of the Teresic development boards for that part have PCIe on board.
Yeah.
Not cheap, however.
Yeah, no, the thing is, the reason why they have hard PCI Express cores is because after plug-in into the computer, they have to respond within 1 or 2 milliseconds. And usually, if you have a big FPGA, loading the configuration takes longer time than those 1 or 2 milliseconds, which would not allow you to plug your FPGA board into a regular x86 board. And this is why they introduced hard cores PCI Express. Yes.
Yep.
Thank you.
Thank you.
Thanks a lot.
Thank you.
Thanks a lot.
I also wonder about the choice to try to develop C to HDL compilers, since C is fundamentally sequential, whereas HDLs are fundamentally parallelized. And I'm just wondering, is there anything out there with converting functional programming languages to HDL, which might be a much better fit?
Yes, there are some attempts at bringing the functional paradigm to programming hardware, but it didn't get any traction outside of academia, unfortunately.
Thank you.
We have a question from the internet.
One question from the internet. Is there wear down in FPGAs, as in do they break over time and how much time?
I have yet to break an FPGA. Well, if you have a flash-based FPGA, obviously you have like only a limited lifetime of like 1,000,000 years before the configuration gets lost, and you can only configure it like a few million times or whatever. There is no known wear down that I am aware of, to be put like this.
Can I freely choose the hardware description language I want to use, or am I bound to special tools from the vendors?
Let's put it this way. Most vendors support via Verilog and VHDL. A little bit different each one, so that sometimes they're not compatible. And what they also support is netlist, edif netlist. So most of the tools are either generating either of those three, so that you can use them. For example, PSHDL is generating VHDL code, so that you can use it with any vendor tool that you want.
Thank you.
There any hope for FPGA development boards to drop in price towards the microcontroller range, or is the support for programming too complex?
Let's put it this way. On my PSHDL board, there is an XMega which is programming the FPGA, and so I think there are some lower bounds if you don't want to be subsidized by the vendor. I think really that 30 euros is a very lower bound of where you can create a board that is interesting and has an FPGA that does something interesting. So it will never. I don't think that it will ever be suitable to say, oh no, instead of using an Atmel, I will use an FPGA.
Is it possible to recode the NAND fields at runtime so that you got a kind of self-modifying FPGA?
Well, if you ask the vendors, yes. If you try it in practice, it's like, well, no. In theory, it's possible to reconfigure the FPGA while it is running. I was talking with some vendors, and they said like, but it's not like you can change the configuration like every millisecond, which would be really interesting and awesome. But it's more like, they are like, you can have change it like one time in a minute or so. So it will take 1
minute.
You have to configuring takes some time, and it takes like with a big FPGA, it can take like 1 or 2 seconds, and you need to have time to compensate for that. Okay. So yeah, so in theory you can do that. In practice, I haven't seen it yet in a practical application outside of a vendor demonstration.
Thanks.
Do we have any more internet questions? In that case, we are done, and please thank the speaker again.